Voyager 1 has already escaped the solar system. Andromeda hangs in the sky as our nearest big galactic neighbour. So the obvious question hits, when do our fastest machines actually get there? In this video, we're going to run that question all the way out, from the real distance and Voyager's true speed, to the insane timescales you almost never hear said out loud. How far away is Andromeda? In numbers that actually hurt to hear. Not in vague millions of light years talk, but in hard distance and hard time, the kind where your normal sense of far just stops working. Andromeda, the nearest big galaxy to us, is about 2.5 million light years away. A light year is the distance light travels in 1 year, moving at about 300,000 kilometers every second, around 186,000 miles per second. So when we say 2.5 million light years, we're saying this. Light has to move at its absolute maximum speed, with no breaks, for 2.5 million years straight to get from here to that galaxy. Now drop the word light year and turn it into kilometers. That distance is roughly 24 quintillion kilometers. Say it as a number, that's a 2, a 4 and 19 zeros after it. In miles, it's about 15 quintillion. These are not numbers you use in daily life. You'll never see them on a bill, a clock or a car dashboard. They only show up when you're talking about galaxies. Let's bring that down to a speed you understand, a simple road speed. Take a car doing 100 kilometers per hour, around 62 miles per hour. Hold that speed perfectly, never stopping, never refueling, never sleeping. To cross 24 quintillion kilometers at that pace, you're looking at on the order of 270 trillion years of driving. A human lifetime is maybe 80 years, so you'd need something like 20 trillion lifetimes back to back just to arrive. Already, the important point is clear, your normal sense of distance is not built for this. You can think in kilometers from one city to another, maybe a flight around the planet. 2.5 million light years is on a completely different tier. It is not just a long way, it is a scale where even the longest human story you can imagine is basically zero. Now, light itself. In your house, light feels instant. You switch on a lamp, the room is bright, no delay. Even from the moon to Earth, it's only around 1 and a bit seconds. From the sun to Earth, just over 8 minutes. Those still feel pretty quick. But at the Andromeda distance, that same light, at that same maximum speed, needs around 2.5 million years to complete the trip. Every photo you've ever seen of Andromeda shows you that galaxy as it was roughly 2.5 million years in the past. When that light left those stars, there were no cities, no writing, no internet. Our entire species was in a very different stage. So when people say the speed of light is the cosmic speed limit, that's correct. But here's the twist. Even the speed limit looks slow once you stretch space this much. That's the first crack in your intuition. If the fastest thing allowed in the universe needs millions of years, where does that leave a physical spacecraft? Next, compare this distance to the size of our own galaxy, the Milky Way. The bright, star-filled disk of the Milky Way is around 150,000 light-years across. Andromeda sits 2.5 million light-years away. If you lined up Milky Way-sized disks in a row, you'd need about 17 of them to bridge that gap. So to get from us to Andromeda, you're asking a probe to cross a distance about 17 times the full width of our own galaxy's main disk. In more normal units, scientists like to write that as about 2.4 times 10 to the power of 19 kilometers. That's useful on paper, but for spoken language it helps to keep two simple anchors in your head, around 24 quintillion kilometers in metric, around 15 quintillion miles in imperial. Metric is the precise tool here. Miles just back it up in more familiar everyday numbers, especially if you're used to thinking in miles per hour from cars and planes. Let's use one more scaling trick that keeps things concrete. The distance from Earth to the Moon is about 384,000 kilometers, around 239,000 miles. If we say that in a simple model, this Earth-Moon distance is 1 meter, the length of your arm, then at that same scale the distance to Andromeda becomes about 60,000 kilometers. That's around 1.5 times the distance all the way around Earth's equator. So on this scale, Earth and Moon fit comfortably on your desk, but Andromeda still sits an entire planet away. In that same model, with that same scaling, Voyager 1 right now would barely be a tiny fraction of a millimetre away from the Earth position. Not even close to the Moon, nowhere near the edge of your desk. So you, versus 2.5 million light-years, is a mismatch. Human lifetimes, human history, human technology, everything you know, sits on timescales of seconds, hours, years, maybe thousands of years. Here we are talking about millions of years just for light, and tens of billions of years for a slow probe. That's why this is not just a big distance, it's a distance that breaks the way you normally think about time. Now bring in Voyager 1 for the hook that drives this entire video. Voyager 1 is fast. Relative to everyday life, it is extremely fast. It's moving at about 17 kilometers per second, that's roughly 61,000 kilometers per hour, or about 38,000 miles per hour. At that speed, it could cross the diameter of Earth, about 12,700 kilometers, in roughly 20 minutes. That sounds ridiculous compared to a car or a jet or a bullet. So here is the real question sitting under everything we're going to do next. If a spacecraft that can cross our entire planet in 20 minutes is flying out into deep space, how long does it need to cross the gap to Andromeda, which is not one Earth diameter, not one Sun-Earth distance, but 2.5 million light-years, about 24 quintillion kilometers? Are we talking billions of years, tens of billions of years, or something even worse? Right now, knowing the raw distance, you can feel that the answer will not be friendly. But to see how extreme it gets, you need the other half of the problem, the actual speeds and positions of Voyager 1 and Voyager 2. Once you see how fast they really go, and how far they've actually managed to get in about 50 years, the Andromeda distance stops being just a big number, and turns into a clear, brutal verdict on what our current technology can and cannot do on a galactic sun scale. So now that you know how ridiculous the distance to Andromeda really is, the next question is simple but brutal. What exactly are we hurling into that kind of space, and how fast is it actually going? Voyager 1 is not a slow machine. It cruises at about 17 kilometers every second relative to the Sun. That's around 61,000 kilometers per hour, or about 38,000 miles per hour. Put that next to things you know and the gap is huge. A typical passenger jet moves at around 900 kilometers per hour, maybe 550 miles per hour. Voyager 1 is roughly 70 times faster than that. A rifle bullet might leave the barrel at about 1 kilometer per second, give or take, so Voyager is something like 50 times faster than that. On any normal scale, this is not just a fast spacecraft. It completely roasts almost every speed you have seen in your life. But speed without location is abstract, so lock in where they actually are. Right now, Voyager 1 sits roughly 25 to 26 billion kilometers away from Earth. In miles, that's around 16 billion. In the units astronomers like to use, that's about 170 astronomical units. 1 astronomical unit, or AU, is the average distance from Earth to the Sun, about 150 million kilometers, or 93 million miles. So Voyager 1 is around 170 times farther from the Sun than Earth is. At that distance, light itself takes about 24 hours to travel from the spacecraft back to Earth. When Mission Control sends a radio command at the speed of light, it spends an entire day crossing that gap. For the first time, we are hitting a scale where one light day is not a thought experiment. It is literally where your hardware is sitting. Voyager 2 is a bit closer in, but still way out compared to the planets. It's around 21 billion kilometers away, about 13 billion miles, at a distance of roughly 143 astronomical units. It moves a little slower than Voyager 1, but the key point is the same. Both probes are far beyond the region where planets orbit, deep into the outer territory of the Sun's influence, and still, if you overlay that on the Andromeda distance, both of them are basically glued to the starting point. So what does that 17 kilometers per second actually buy you over time, if you keep it up for years? Voyager 1 covers roughly 3.6 astronomical units in 1 year. That means every year it adds about 3.5 Earth-Sun distances to its total. That sounds huge when you think of just the solar system. 3.5 astronomical units per year is more than enough to blow past the orbits of the outer planets and never come back. But compare that to a light year. 1 light year is about 63,000 astronomical units. If you're only logging 3.6 astronomical units per year, then each year you cover around 0.00006 of a light year. That is 600 thousandths of a light year per century. On the scale of galaxies, that isn't effectively standing still. Here's the conflict you need to feel. On a human scale, 17 kilometers per second is insane. On a planetary scale, it's impressive. On a galactic scale, it is close to 0. When we later talk about tens of billions of years to Andromeda, this number, 3.6 astronomical units per year, is the quiet reason why. Now, to really understand why the Voyagers behave the way they do, you have to look at what they were actually built for. They were never meant to be galaxy-crossing ships. The design goal in the 1970s was clear and very local: ride a rare gravitational lineup of the outer planets, hit multiple flybys with as little fuel as possible, and then keep going to sample the edge of the sun's bubble. That grand tour used gravity assists from Jupiter and Saturn for both probes. For Voyager 2, it also included Uranus and Neptune. Each planet's gravity bent the path of the spacecraft and pumped up its speed without burning massive amounts of propellant. The engineering problem was launch on time, thread those flybys with very precise timing, survive intense radiation around Jupiter and Saturn, and send back data and pictures of worlds we had never seen up close before. That's what their propulsion and navigation systems are built around: not long, controlled burns that point them at another galaxy. Past the planets, the target region was the heliosphere, the big magnetic and particle bubble blown by the sun's wind. Inside that bubble, the solar wind dominates. Outside, you're in the local interstellar medium filled with particles and magnetic fields that belong to the galaxy, not to our star. Voyager 1 has already crossed the boundary called the heliopause and is now sampling interstellar space. Voyager 2 has done the same. When you hear about them, you'll often hear phrases like first human-made object in interstellar space. That's true, and it's the core of their mission now: measure how the particle environment changes, how cosmic rays behave, how dense the plasma is as they move away from the sun. And running alongside all that science is the part most people remember: the golden records. Each spacecraft carries a 12-inch gold-plated copper disc with sounds and images from Earth. There's music from Bach to rock and traditional songs. There are greetings in 55 languages. There are pictures showing basic human life, landscapes, diagrams, and simple scientific information. The idea was not, "We're coming to visit you soon." It was more honest and more modest. We were here at this time on this world, and this is what life looked like for us. From a practical point of view, the odds that anyone ever finds one of those records are tiny, because the volume of space they pass through is so huge, and the spacecraft themselves are so small. But as part of the mission design, they matter in a different way. They mark the Voyagers as time capsules, not just tools. These aren't just sensors and antennas, they're also physical proof that a technological species once reached this level and decided to send a trace of itself outward, even if no one ever listens. So combine all of that. You have a pair of spacecraft moving tens of times faster than bullets, far beyond the known planets, just brushing past the edge of the sun's protective bubble, carrying messages that could, in theory, survive for billions of years. On the scale of a human life, that's already extreme, but here's the tension. Even with those speeds, and even with those distances already covered, they have barely scratched a fraction of a single light year, while Andromeda sits 2.5 million light years away. That sets up the next step we have to take. Before we can talk seriously about reaching Andromeda, we need to look at the home field, the full size of the Milky Way, the way the sun orbits inside it, and where the Voyagers sit in that structure. Once you see how small their path is compared to our own galaxy, the question about them crossing to another galaxy starts to look even more extreme. How big is the home field you're actually playing on when you throw something like Voyager out into space? Because until you feel the size of our own galaxy and the size of Andromeda, it's easy to think these probes are already far along the path. They're not. Start with the Milky Way. The bright disk of our galaxy is roughly 150,000 light-years across. That means if a beam of light started on one edge and went straight across to the other edge, it would need 150,000 years, moving at 300,000 kilometers per second, about 186,000 miles per second, just to get from side to side, and that's just our galaxy. Andromeda is bigger. Estimates put its diameter somewhere around 200,000 to 260,000 light-years. So if the Milky Way is already huge, Andromeda stretches that out even more. You're not looking at a cluster of a few stars here. You're looking at giant rotating systems with hundreds of billions of stars each. Gas, dust, dark matter, all bound together by gravity. These are full galactic structures, not local neighborhoods you cross in a weekend. Now zoom out one more level, because the Milky Way and Andromeda are not isolated. They sit in a small galaxy group called the Local Group. Along with a third major galaxy, Triangulum, and a bunch of smaller dwarf galaxies, they're all bound together in a shared gravitational cage. So when someone says reach Andromeda, they're really talking about crossing space inside this shared gravitational well, moving from one big mass at one side of the group to another big mass at the other side. That is not just interstellar space between stars in one galaxy. That is intergalactic space, the sparser region between the main galaxy disks, still under the combined pull of all that mass. Keep that picture in mind and now place the Voyagers in it. Right now, they feel far because they're tens of billions of kilometers from Earth. Voyager 1 is now around 25 to 26 billion kilometers out. Voyager 2 is around 21 billion. In astronomical units, that's roughly 170 astronomical units for Voyager 1, 143 astronomical units for Voyager 2. That sounds huge, and for solar system work it is, but on the full Milky Way scale, these numbers are microscopic. Even after about 50 years of travel, Voyager 1 has not left the Sun's extended comet reservoir. It has crossed the heliopause, so it is outside the solar wind, in the local interstellar medium, but it is still inside the broader region where the Sun's gravity dominates small icy bodies, a region that includes the Oort cloud. The inner edge of the Oort cloud is expected to sit thousands of astronomical units out, not hundreds. At Voyager 1's current speed, it would need roughly 300 more years to reach that inner Oort cloud region, and on the order of 30,000 years to pass fully beyond the outer edge. So right now, in galactic terms, it has barely taken a step off the driveway. Now take the Sun's motion into account, because that sets the background frame. The Sun is not sitting still while Voyager drifts away. The entire solar system orbits the center of the Milky Way at around 220 kilometers per second, close to 490,000 miles per hour. One full orbit, one galactic year, takes roughly 230 million Earth years. So while you think of Voyager heading straight outward, what's really happening is this. The whole solar system is racing around the galaxy, dragging Voyager along, and Voyager's 17 kilometers per second is just a small adjustment added on top of that huge orbital motion. This matters for the Andromeda question, because any travel between galaxies is happening inside this moving, rotating frame. You don't just have a probe going in a straight line through empty stillness. You have a tiny spacecraft, with a small speed relative to the Sun, riding on a star that itself is moving hundreds of kilometers per second around the galaxy, inside a group of galaxies that interact gravitationally with each other. So step back and stack the numbers. Milky Way, 150,000 light-years across. Andromeda, around 200 to 260,000 light-years across. Distance between galaxy centers, about 2.5 million light-years. Voyager's current distance from the Sun, around 170 astronomical units, which is about 0.0027 light-years. And it will still need tens of thousands of years just to fully exit the Sun's distant comet cloud. Beside that, the local group extends over millions of light-years. You can say it directly when you ask, when do Voyager 1 and Voyager 2 reach Andromeda? You're effectively asking, When does a tiny velocity tweak on top of the Sun's galactic orbit, applied to an 800 kilogram spacecraft, allow it to cross millions of light years of intergalactic space inside a moving, evolving galaxy group? It is not just a hard trip, it is the wrong tool for that job by many, many orders of magnitude. This is why the Andromeda question sounds simple, but collapses as soon as you put the numbers next to each other. The probes are impressive inside the solar system, and even on the scale of the heliosphere, but on the scale of the Milky Way and Andromeda, they are basically stuck in the extreme inner zone near the Sun, scratching centimetres of progress on a map that is millions of kilometres wide if you shrink it to a human scale. So now there's a clear gap in your understanding that we need to close, because you've heard a mix of units, kilometres, astronomical units, light years, light days, and they all blur together after a while. To really feel how hopeless the Andromeda trip is for the Voyagers, you need clean stepped units, one for the solar system, one for nearby stars, one for galaxies. Once those units are in your head and you see how slowly Voyager climbs them, the time scale for getting to Andromeda stops being just a shocking number and turns into something you can logically follow, rung by rung. You keep hearing astronomical unit, light day, light year, but do those actually line up in your head as real steps on a ladder? Or are they just different ways of saying very far? This is where we turn them into real numbers, and when we do, Voyager's trip to Andromeda goes from unlikely to basically frozen. Start with the simplest rung, the astronomical unit, or a U. One astronomical unit is the average distance between Earth and the Sun. That's about 150 million kilometres, roughly 93 million miles. That's the basic yardstick of the solar system. Mercury is a bit over a third of an AU from the Sun. Mars is about 1.5 AU. Jupiter sits around 5 AU. Neptune around 30 AU. When we say Voyager 1 is out at about 170 astronomical units, we're saying it's 170 times farther from the Sun than you are right now. Turn that into plain numbers. 170 astronomical units is around 25.5 billion kilometres, about 16 billion miles. That is already far beyond the Kuiper Belt, the region of icy bodies beyond Neptune that includes Pluto. So yes, Voyager 1 has cleared the main planet zone and the known dwarf planet zone, but it is still deep inside the Sun's long-range gravitational influence. The Oort cloud, the huge spherical shell of comets, likely starts thousands of astronomical units out and extends tens of thousands of astronomical units. On this scale, 170 astronomical units is just past the inner edge of the Sun's front yard. Now move up one rung to a light day. A light day is the distance light travels in one day. Light covers about 300,000 kilometres every second, and there are 86,400 seconds in a day. So you end up with a distance of roughly 26 billion kilometres, about 16 billion miles. That means one light day is almost exactly the kind of distance Voyager 1 is approaching. Around the mid-2020s, roughly 2026 to 2027, Voyager 1 is basically one light day from Earth. A radio signal sent from the spacecraft at the speed of light will take about 24 hours to reach the deep space network on Earth. A command from Earth takes another 24 hours to get back. That sounds enormous, and inside the solar system it is. A full day of light travel time is nothing like the delays you get from Mars or Jupiter, which are minutes to hours. But here's the critical detail. One light day is just one out of about 1,460 slices that make up a single light year. Divide a year into days, that's where the number comes from. So if you think of a light year as a 1,460 step staircase, Voyager 1 has climbed roughly one single step. Andromeda is 2.5 million of those staircases laid end to end. So we need the next rung, the light year itself. One light year is about 9.46 trillion kilometres in metric and about 5.88 trillion miles. Keep those two numbers, 9.5 trillion kilometres, nearly 6 trillion miles. This is the standard unit once you start talking about distances between stars and between galaxies. Now plug Voyager 1's speed into that. At around 17 kilometers per second, or about 38,000 miles per hour, how long does it take to cover one light year? Do the rough math in words. In 1 second, Voyager covers 17 kilometers. In 1 hour, that's about 61,000 kilometers. In 1 day, it racks up a bit over 1.5 million kilometers. Stretch that out over a full year and you end up with tens of billions of kilometers. Compared to 9.46 trillion, that's tiny. When you divide distance by speed properly, you get a travel time on the order of 18 to 20,000 years for Voyager 1 to move just 1 light year at its current speed. So now you have a clean, simple conversion in your head. 1 light year costs Voyager 1 roughly 20,000 years. That's your key number. Remember it, because everything else is just multiplication. Take that cost and scale it to Andromeda. The galaxy sits about 2.5 million light years away. Multiply 20,000 years per light year by 2.5 million light years, and you land at around 50 billion years. That's the timescale for a Voyager-class probe, moving at 17 kilometers per second to cover the raw distance to Andromeda, if it were perfectly aimed and nothing slowed it down. The age of the universe right now is about 13.8 billion years. So you are asking a spacecraft built in 1977 to keep flying for roughly 3 to 4 times the entire age of the universe so far, just to make that one trip. This is the moment where the numbers stop feeling like hard sci-fi and turn into this is basically never on any human scale. You can talk about 50 billion years, but no civilization we know, no technology we have, and no records we keep makes sense over that span. It's not just longer than human history, it's longer than the lifetime of many types of stars. To hammer the scale one last time, use a simple physical model. Take the distance from Earth to the Moon, about 384,000 kilometers or 239,000 miles. Call that distance 1 meter. On this model, the Earth-Moon separation is the distance from one of your hands to the other. Now, scale everything else so that 1 meter equals that Earth-Moon distance. At that same scale, the distance to Andromeda becomes roughly 60,000 kilometers. That's about 1.5 times the full distance around Earth's equator. So in this scaled-down universe, Earth and Moon are a 1 meter gap on your desk. Andromeda is 60,000 kilometers away. Voyager 1, at around 170 astronomical units, translates into just a few hundredths of a millimeter away from the Earth point along that 1 meter Earth-Moon line. Not a meter, not half a meter, not even a millimeter, just a tiny offset from the starting dot. Everything it has done so far is a sub-millimeter nudge in a universe where the target is tens of thousands of kilometers away. Now line all these rungs back up. 1 astronomical unit, 150 million kilometers. 1 light day, 26 billion kilometers, about where Voyager 1 is now. 1 light year, 9.5 trillion kilometers, which costs Voyager about 20,000 years. Andromeda, 2.5 million of those light years, demanding about 50 billion years of travel. When you hear someone casually ask, so when do Voyager 1 and 2 reach Andromeda? This is the ladder they are really climbing, often without realizing it. But you might still be thinking, okay, fine, the timescale is insane, but what if you really did point Voyager straight at Andromeda? No detours, no curves, just a pure straight line shot? Does the answer somehow get better if we pretend we can aim it perfectly? That's the next step. And that's where the straight line fantasy gets crushed by the raw division of distance by speed. So here's the brutal question. If you stripped away all the messy details and just pointed Voyager 1 straight at Andromeda, at its current speed, does the answer suddenly become less insane, or does it get even worse? Start by assuming something that is already impossible. Perfect aim. Right now, Voyager 1 is not heading toward Andromeda at all. To make it do that, you would have to rotate its entire path in space so that its direction lines up exactly with the center of the Andromeda Galaxy, without really changing its speed. That sounds simple in words, but in engineering terms, it means giving the spacecraft a huge change in velocity, what engineers call delta V. We're talking about a speed change on the order of many kilometers per second. Voyager's tiny thrusters are only meant to twist the spacecraft for pointing its antenna, not to re-aim its whole trajectory by tens of degrees, so already the setup is science fiction. You're giving Voyager a steering and propulsion upgrade it does not have, but let's grant that for a moment, because the straight line fantasy is useful. Suppose Voyager 1 is now perfectly lined up with Andromeda, still moving at about 17 kilometers every second, around 61,000 kilometers per hour, about 38,000 miles per hour. How long does it take to cross the raw distance? The distance we're dealing with is about 2.5 million light years. In meters, that is on the order of a number with 22 zeros after it. In other words, take a 2, then a 3, then a 6, and put 21 or 22 zeros behind it, and you are in the right ballpark for meters. Voyager's speed in meters per second is around 17,000, so you take that huge distance and you divide by 17,000 meters per second. The result is a time in seconds with 18 zeros in it. When you then convert that many seconds into years, by dividing by about 31.5 million seconds per year, you land at roughly 44 billion years of travel time. And when you take into account that we are rough with the distance and speed, and we are ignoring any slowdowns or complications, rounding that up to around 50 billion years is completely fair. So just in cold, straight arithmetic, the straight line trip at Voyager 1's current speed is on the order of tens of billions of years. Not millions, not a few billion, but something like 4 to 5 times 10 billion. That is the answer even in the most generous, unrealistic version of the story, where you give Voyager magic steering and a perfectly clean shot. Now compare that to the big clock we actually live in, the age of the universe. All current observations point to a universe that is around 13.8 billion years old. That's the time from the Big Bang to now. All of cosmic history, the first stars, the first galaxies, the formation of the Milky Way, the birth of the Sun and Earth, the rise of life, everything humans have ever done fits into that 13.8 billion year block. Voyager 1, in our straight-line fantasy, needs more than 3 times that entire block just to reach Andromeda. So when you frame it that way, you're basically asking a 1977 spacecraft to remain intact and on course for a span of time that makes the whole history of the universe so far look like the opening chapter. And this is under a fake condition that the universe does not change while this is happening. In reality, over tens of billions of years, things do change. Stars are born and die, galaxies interact, drift and merge, orbits shift, gas is used up, dark energy keeps stretching space. The map itself is moving under you while you fly. Over 50 billion years you are not flying through a fixed backdrop with a target locked in one position. You're moving through a dynamic universe that keeps evolving. So the simple calculation is already generous to Voyager. Reality would likely make the trip even more complicated and less clean. What about Voyager 2? It starts off worse. Voyager 2 moves more slowly than Voyager 1 at about 15.4 kilometers per second, roughly 35,000 miles per hour. That speed difference sounds small, but over huge distances it matters. If Voyager 1 needs around 20,000 years to travel 1 light year at 17 kilometers per second, Voyager 2 needs more, somewhere near 19,000 to over 20,000 years per light year. Multiply that by 2.5 million light years, and you get a travel time that is even longer than Voyager 1's, still in the same tens of billions of years band, but always lagging further behind. Over time, that gap grows. After 1 million years, Voyager 2 will be millions of kilometers, then billions of kilometers behind Voyager 1. After 1 billion years, the separation between the two craft will be measured in light years. They are both impossibly slow for galactic travel, but one is always losing the race even inside that slow-motion disaster. All of this directly attacks your sci-fi trained intuition. Movies and shows often show starships punching across a galaxy in hours or days. You hear someone say warp or hyperspace, and instantly jump to an idea that going to another galaxy is basically like a long-haul flight with better engines. The Voyagers expose how far that picture is from reality with today's technology. 17 kilometers per second is already way beyond anything humans ride on. It is tens of times faster than bullets, much faster than any plane, way beyond any car or rocket once it stops thrusting. And still on the Andromeda scale, that speed might as well be written as 0. So the correct word here is not just hard. Intergalactic travel with present-day propulsion is effectively frozen. The timescales are so much larger than any realistic mission duration, any human planning horizon, or any machine lifetime, that from our point of view, the event Voyager reaches Andromeda is not just unlikely, it is outside the range of events that matter. It exists only as a math answer on paper, not as something that can ever show up on a mission timeline. And remember, everything we just did is still optimistic. We pretended we could rotate Voyager perfectly toward Andromeda. We pretended its speed never changes, its structure never decays, and the universe stays simple. In the real situation, it's worse, because Voyager is not even aimed at the target. It is heading in a completely different direction, set by gravity assists from planets decades ago. If you want the full, honest picture, you now have to drop the straight-line fantasy and look at where these probes are actually going in the sky and what that does to the idea of them ever arriving at Andromeda. If the raw travel time wasn't already bad enough, there's a harsher detail. The Voyagers aren't even pointing anywhere near Andromeda in the first place, and they never will. On the sky, Voyager 1 is heading roughly in the direction of the constellation of Fucus. Voyager 2 is heading toward the constellation Telescopium. Andromeda, the galaxy you're asking about, sits in a completely different patch of sky, in the constellation Andromeda, in the northern hemisphere. These constellations are just patterns of stars, but astronomers use them as a coordinate grid. When you say it's going toward a Fucus, you're really saying the spacecraft's path is aimed in a specific direction in three-dimensional space. None of those paths line up with the direction to Andromeda. Not slightly off, not close enough over millions of years, they are completely different vectors. That misalignment is not an accident, and it's not something you can just correct with a small steering burn. It was baked in from the very start. The Voyagers were launched in the late 1970s to exploit a rare alignment of the outer planets, a configuration that only comes around every 175 years or so. In that window, Jupiter, Saturn, Uranus and Neptune lined up in a way that allowed a single spacecraft to fly past one planet, swing around it and use its gravity to gain speed and redirect its path toward the next planet, then do it again and again. Those gravity assists were the whole point. Voyager 1 flew past Jupiter and Saturn. Voyager 2 flew past Jupiter, Saturn, Uranus and Neptune. Every flyby changed the spacecraft's direction and speed, but in a very controlled way. Mission designers chose those paths to hit the right targets at the right times, to get the best science return, and to still give the probes enough speed to escape the inner solar system afterward. The final exit directions, the ones they're on now, are simply the result of those carefully chosen swingbys. Nobody was planning an Andromeda trip, that wasn't even on the table. So when you ask, why don't we just turn Voyager toward Andromeda now? What you're really asking for is a massive change in direction, applied to a craft that has almost no ability to change its overall velocity. If you want to pivot a spacecraft moving 17 kilometers per second by tens of degrees, you need a change in velocity delta V that is a big fraction of that speed. Even a 10-degree turn at that speed is not cheap. To bend the path by something like 30 degrees, you're talking about a delta V of several kilometers per second. That's thousands of meters per second of extra speed change. Voyager's propulsion system is nowhere near that level. The thrusters on board use hydrazine and are designed for attitude control, which means they turn and steady the spacecraft, so the antenna stays locked onto Earth and the instruments point where they need to. The total change in speed those thrusters can produce over the entire life of the mission is tiny compared to 17 kilometers per second. We're talking about centimeters per second, maybe a bit more, not thousands of meters per second. They're like nudging the nose of a car while it's rolling, not installing a new engine. On top of that, fuel is almost gone. After decades in space, a lot of hydrazine has already been spent on keeping the antenna properly pointed as the spacecraft rolls and drifts. The mission now is about squeezing the last bits of control out of what's left, not about big trajectory changes. There is no spare propellant sitting there waiting for a giant course correction toward another galaxy. The design philosophy matters here. These are flyby probes, not deep space cruisers with huge main engines. Their launch vehicles, the Titan Centaur rockets, did the heavy lift at the start. The planets did the rest with gravity. Voyager itself has no large main engine for go-there-now burns. It has attitude thrusters, essentially space-rated maneuvering jets for pointing, not long-duration high-thrust engines. If you wanted a mission that could deliberately aim for another galaxy, you would not build a Voyager. You would start with a propulsion system that can deliver a large fraction of light speed, or at least a significant fraction of the galaxy's escape speed, and you'd give it enough propellant, power, and control to manage huge changes in velocity and direction. None of that exists on these 1970s probes. So even before you get to the insane travel times, you hit a basic directional wall. The probes are on fixed, unpowered trajectories set by past gravity assists. In practical terms, they are bullets that left the gun decades ago. You can spin the bullet, you can't grab it and send it to a different city halfway through the flight. The only reason they still do anything is because their instruments are still measuring and their antennas can still talk to Earth, for now. There's another hidden consequence to their real trajectories. Because they're heading in these fixed directions, what they actually probe in the galaxy is not some straight line toward another major galaxy, but a small slice of our own galactic environment. Voyager 1 will head into one region of the Milky Way's outer disk and halo. Voyager 2 will drift into another. Over tens of thousands of years, they will pass relatively near a few stars. They'll keep orbiting the galactic center with the Sun, and they'll move slowly outward relative to the Sun's position. None of that motion naturally lines them up with Andromeda. That leads to the real question that astronomers care about in the far future. It's not when do they reach Andromeda. The honest version is, where in the Milky Way's outer regions, in the halo around our galaxy, will these probes be drifting when the Milky Way and Andromeda start to seriously interact gravitationally? Because on billion-year timescales, the Big Show is not a tiny probe crossing an impossible distance. It's two entire galaxies feeling each other's pull, starting to shift orbits and possibly merging. To understand why the Voyagers are trapped in that story, you have to think in terms of escape speeds and gravity wells, not just raw travel time. They have enough energy to escape the Sun, but they are nowhere near fast enough to escape the Milky Way's grip. Until you see that clearly, it's easy to imagine them just coasting away to Andromeda. Once you bring in galactic escape velocity, it becomes obvious they are permanently stuck in our own galaxy's deep gravity field. So the tension ramps up again, because now the question isn't just, are they aimed at Andromeda? We already know the answer to that is no. The deeper question is, even if you pointed them perfectly, do they have anywhere near the energy needed to get out of the Milky Way at all? That's the next step, and the answer there slams the door even harder on the dream of a Voyager ever crossing from one big galaxy to the next. Right now you might be thinking, if Voyager is leaving the solar system, isn't it just leaving everything, including the Milky Way? The short answer is no. It has escaped the Sun, but it is nowhere near escaping the galaxy. Start with the part that sounds like a win, the Sun. Both Voyager 1 and Voyager 2 have what physicists call positive total energy relative to the Sun. That means if you add up their kinetic energy from their speed and their gravitational potential energy from the Sun's pull, the total is above the threshold needed to break free. In simple terms, they are on hyperbolic paths, open curves that never loop back. They are not on closed ellipses like planets and comets that return. They will never fall back into the inner solar system on their own. That's why they are able to push past the heliosphere, past the bubble of solar wind, and move into the surrounding interstellar medium. But now zoom out to the bigger gravity well, the Milky Way itself. Near the Sun's position in the galaxy, the escape velocity. The speed you need to completely break away from the galaxy's gravitational pull is on the order of 500 to 600 kilometers per second. The Sun itself is orbiting the center at around 220 kilometers per second. Voyager 1's 17 kilometers per second is tiny compared to either of those. 17 kilometers per second is roughly 30 to 35 times slower than the speed you'd need to truly escape the Milky Way. What that means is simple and very final. Even though Voyager 1 and 2 are leaving the Sun's grip, they are not leaving the galaxy's grip. Their velocities are just small adjustments on top of the Sun's huge orbital motion. They are, and always will be, gravitationally bound to the Milky Way. They will circle the galactic center, roughly in step with the Sun and the surrounding stars for as long as they physically survive. Here's one comparison that actually helps rather than confuses. Picture a long train racing down a track. The train is the Milky Way. You're inside the train and you toss a small stone down the aisle. That stone can move forward, backward, sideways relative to the inside of the train. It might hit the wall or roll under a seat. But unless it somehow punches through the metal and flies out the window at a huge speed, it stays inside the train and goes wherever the train goes. That's the Voyagers. The galaxy's main orbital motion is the train. The probe's 17 kilometers per second is just the motion of pebbles thrown inside, relative to that much larger motion. If you want a concrete picture of their long-term future, look at specific encounters we can predict. Simulations of their trajectories suggest that Voyager 1 will pass within about 1.6 light-years of a nearby star called Gliese 445 in roughly 40,000 years. 1.6 light-years is still not a direct hit, and 40,000 years is a long time. But notice what's going on. You're not seeing approach another galaxy. You're seeing pass relatively close to a single star within our own galaxy, and even that takes tens of thousands of years. That's the actual scale they operate on. Over tens of thousands of years, they drift enough to come near one star. Over millions of years, they might pass by a few more. Their natural environment is the Milky Way's disk and halo, not the void between giant galaxies. They are part of the slow internal motion of one galaxy, not projectiles that can jump from one big system to another. Now connect this straight back to Andromeda. To genuinely leave for Andromeda, you would first have to give a spacecraft enough energy to climb out of the Milky Way's gravity well. That means pushing its speed up toward the local galactic escape velocity, hundreds of kilometers per second, not tens. Only after you've done that, only after you're no longer bound to the Milky Way at all, does the idea of heading toward another major galaxy become physically meaningful. Voyager is nowhere close. 17 kilometers per second is a great speed for a planetary grand tour. It is a rounding error next to 500 or 600 kilometers per second. So technically yes, the Voyagers are on paths that will carry them for billions of years through the galaxy. They are not going to fall back to the Sun, they are going to keep drifting through the Milky Way's outer regions. But on the question you actually care about in this video, do they reach Andromeda? This entire gravity story slams the door. They can't even get out of our own galactic gravity well, never mind cross the space between big galaxies. And this flips the Andromeda question into its real form. Instead of asking when do they arrive in that other galaxy, the more honest version is, where will they be inside the Milky Way's outer halo when the Milky Way and Andromeda start to seriously interact and maybe merge billions of years from now? Because on that timescale, it's the galaxies that move toward each other, not the probes leaping across the gap. To feel just how tiny and fragile those probes are in the environment they're moving through, the next step is to look at the medium itself, what interstellar and intergalactic space are actually like, what they're filled with, and how that affects something as small and slow as Voyager over unimaginable spans of time. Out where Voyager 1 is flying right now, space is not a perfect vacuum. It feels empty, but it isn't. There are a few atoms in every cubic centimetre, mostly hydrogen and helium, along with high-energy particles we call cosmic rays. That thin gas and that radiation are exactly what the Voyagers are measuring. Their instruments count particles, track magnetic fields, log how the plasma density changes as they move away from the Sun's bubble and into the wider environment of the galaxy. So when you hear interstellar space, don't picture a clean, empty void. It's more like a very, very thin gas with radiation constantly washing through it. A few atoms per cubic centimetre sounds like nothing, but when you stretch that over billions of kilometres, it adds up to a real environment. It pushes on the solar wind, it sets the pressure at the edge of the heliosphere, and it slowly interacts with any object moving through it, including our spacecraft. Now go another step out and talk about intergalactic space, the region between big galaxies like the Milky Way and Andromeda. That's even thinner. Instead of a few atoms in a cubic centimetre, you might be talking about a few atoms in an entire cubic metre. So the density drops by a factor of millions. That sounds safer at first, fewer particles to hit you. But it also means there is no realistic gas you can use for braking, refueling or drag-based propulsion. At Voyager's speed, around 17 kilometers per second, or about 38,000 miles per hour, crossing that kind of emptiness is like drifting through a desert where there's nothing to drink and nothing to push against. You just coast, with almost no way to change what you're doing. Even in that thin environment dust and micrometeoroids matter. Space is not only gas, it also contains tiny grains of rock and ice. A dust grain just a millimetre across, hitting the spacecraft at 17 kilometers per second, carries a lot of energy. The kinetic energy scales with the square of the speed, so doubling the speed gives you 4 times the impact energy. At tens of kilometers per second, even a tiny grain behaves in effect like a small projectile. A few hits can chip paint and dent surfaces. A direct hit on a vulnerable spot like a cable or a thin radiator can damage or break it. Right now, the probability of a catastrophic hit on Voyager in any single year is low, because space is very empty and the spacecraft is small. But stretch that out to tens of billions of years, the kind of timescale we got when we tried to send Voyager to Andromeda on paper, and the odds change. Even rare events become likely if you wait long enough. Over that kind of time, the spacecraft is expected to take many impacts, large and small. Panels can chip away, edges can erode, protruding parts can snap. There's no repair crew, no replacement parts, and no way to shield the whole structure forever. On top of collisions, you have radiation and temperature cycling. Voyager's main structure is made of aluminum and titanium, with various composites, insulation, and electronic components bolted and wired together. None of that was designed to shrug off trillions of cycles of heating and cooling or endless exposure to high-energy cosmic rays over billions of years. The mission planners were thinking in decades, maybe a few centuries for the silent drift afterward, not 50 billion years of survival. As the spacecraft spins and moves, surfaces face the sun, then face deep space, though at its current distance the sun is already a very weak heater. Over time, thermal stress makes materials expand and contract again and again. Joints loosen, insulation breaks down, sealants outgas. Electronics are slowly damaged by energetic particles punching through them. Cosmic rays can flip bits in memory, degrade circuits, and slowly alter the properties of materials. On human timescales, this is slow. On billion-year scales, it's totally destructive. There's another problem. The RTGs, the power sources, are constantly putting out heat and radiation too, and they slowly weaken. As the power drops, heaters turn off, electronics get colder, and parts shift to temperatures they were never tested for. Lubricants may freeze or degrade. Structures may become more brittle. Even if the trajectory could, in theory, continue unchanged for tens of billions of years, the hardware itself is not built to endure that span. Long before Andromeda is even noticeably closer, the Voyagers are almost certainly just dead metal fragments, with no functioning instruments, no working memory, and no coherent structure. So reaching Andromeda is not only a timing problem, it's a materials problem. It's asking 1970s aluminum, titanium, solder, plastic, and electronics to survive continuous exposure to radiation, dust, and temperature swings longer than stars like the sun will live. On that timeline, everything cracks, erodes, and disintegrates. You're not dealing with a solid, stable object that just flies forever. You're dealing with something that ages rapidly on cosmic terms. If you try to picture what Voyager looks like even a few million years from now, never mind tens of billions, the honest answer is that it probably doesn't look like a clean spacecraft at all. Antennas break, booms snap. The golden record cover might get pitted and scarred. The structure might fragment. At some point, what's left is just an odd-shaped, partially radioactive lump of processed metal drifting through space, with no power and no ability to tell anyone where it is. That's why when you talk about Andromeda and the Voyagers in the same sentence, you can't only talk about distance and speed. You have to ask, can this machine even physically survive the journey as an intact object? The answer is almost certainly no. The timescales we computed earlier assume a perfectly rigid, eternal spacecraft that never changes. Reality gives you dust, radiation, temperature stress, corrosion-like processes in vacuum, and mechanical fatigue. All of those eat away at the structure, piece by piece, which leads to a very sharp reality check. The limit on Voyager is not just how long it would take to flaunt to another galaxy. The real limit is much closer and much more practical. How long can it even keep its lights on, its instruments powered, and its transmitter working before it goes silent forever? Because that talking lifetime is not in billions of years, it's in decades from now. To answer that, you have to look straight at the power system, the radioactive generators, and the slow countdown they're already in. That clock kills the mission long before the Andromeda timescales even start to matter. How long can a spacecraft keep talking when its power source is literally decaying away? Atom by atom, no refuel, no repair, nothing. Because this is the hard stop on Voyager's story long before any journey to Andromeda even begins to matter. Both Voyagers run on RTGs, radioisotope thermoelectric generators. Inside those, you've basically got chunks of plutonium-238, a radioactive material that gets hot as it decays. That heat flows through thermocouples, solid-state devices that turn a temperature difference into electricity. At launch, each spacecraft had RTGs producing around 470 watts of electrical power, like a few bright household light bulbs combined. That doesn't sound like much, but in deep space, with careful engineering, it's enough to run instruments, heaters, computers, and a high-gain radio. But plutonium-238 has a half-life of about 87.7 years. That means every 87.7 years, the radioactive power output drops by half, and the thermocouples themselves also degrade over time, so the electrical output falls even faster than the pure decay law would suggest. Year after year, the available power shrinks. The RTG heat is still there, but the conversion to electricity gets less and less efficient. The result is simple. Every system on board has to live on a slowly shrinking energy budget with no way to boost it back up. To keep the mission alive, NASA has been playing a long, careful power triage game. Instruments have been turned off one by one to save a few watts each. Some of the cosmic ray detectors, low-energy charged particle instruments and other sensors have already been shut down permanently. Each switch off extends the life of whatever remains. Right now, only a small set of key instruments are still running on each Voyager, chosen to maximize the science you can get from the edge of the heliosphere and the local interstellar medium with the few tens of watts still available. Even the heaters have been rationed. In some cases, instruments are being run colder than their original design limits because the power to keep them warm just isn't there anymore. It's a controlled slide down a slope towards zero, where the mission team constantly decides, what can we afford to lose next, without killing the critical data flow? Projecting forward, the numbers point to a clear end to the talking phase. In the 2030s, the RTG output drops to the point where there simply isn't enough electrical power to run any instruments plus the transmitter. The best estimates put at least one instrument surviving into the early to mid-2030s, but by somewhere around 2035 to 2036, there likely won't be enough power left to drive the big radio that beams data back to Earth. At that point, the spacecraft might still exist, might still be drifting, but from our point of view they are gone. No signal, no telemetry, no new measurements, just silence. There is no solar backup waiting in the wings. At distances of 170 astronomical units and beyond, sunlight is extremely weak. the intensity of sunlight drops with the square of the distance, so at 170 astronomical units, it's about 1 over 170 squared, or roughly 1 over 30,000 of what you get at Earth. Solar panels out there would produce tiny currents for huge panel areas and mass. Back in the 1970s, that simply wasn't practical. The Voyagers were designed as pure nuclear-powered missions. Once the plutonium output falls below a certain threshold, that's it. There is no second power source to switch to, no batteries that magically recharge, nothing. So from a power perspective, the mission has 2 phases, a short talkative phase that lasts a few decades, and then a very long dead drift phase that lasts as long as the hardware physically holds together. We are near the end of the first phase right now. The second phase will outlast human history as we know it, but it will be completely silent. Now, connect this back to Andromeda with real numbers. Earlier, we saw that Voyager 1 needs around 20,000 years to travel a single light year at its current speed, and about 50 billion years to cover the full 2.5 million light years to Andromeda, even in a perfect straight-line fantasy. 1/10,000th of that distance is 250 light years. At 20,000 years per light year, that's about 5 million years of travel time. The RTGs, by contrast, will stop supporting a radio link within the next 10 to 15 years, and the spacecraft will be entirely powerless not long after. That means that by the time Voyager has gone even that tiny fraction of the way, just 1/10,000th, it will have been dark and invisible for millions of years. And if you look at the full 50 billion year trip on paper, the contrast is even sharper. The mission, in any real sense, sending data, running experiments, answering commands, ends in the 21st century, or maybe the 22nd if you're extremely generous about some passive survival. The trajectory, the path through space, continues for tens of billions of years. So you have a mismatch where the operational lifetime is measured in decades, and the hypothetical travel time to Andromeda is measured in tens of billions of years. Almost the entire journey, from our perspective, happens with a dead probe. This is the core twist you have to keep in mind whenever someone talks about Voyagers reaching anything on galactic scales. Physically, the hardware will keep coasting. Energetically, their orbits are stable inside the Milky Way. But as scientific machines, as things that can tell us where they are and what they're seeing, they're on a strict timer set by plutonium decay and thermocouple aging. Nothing about that timer cares about our dreams of intergalactic travel. So in the end, when you put distance, speed, environment and power together, you get a harsh picture. The probes do not have the energy to escape the galaxy. They are not aimed at Andromeda. They move through space that slowly tears hardware down, and their power system will shut them up completely within the next couple of decades. The path they trace through the galaxy is interesting. The idea of them ever arriving in another major galaxy is not. But there's still one more layer that makes this whole question even more unstable. We've been treating Andromeda like a fixed target, sitting in one place waiting for us. It isn't. That galaxy is moving too, and not slowly, and its long-term future relative to the Milky Way is not a simple static distance problem. Once you bring in the fact that Andromeda is actually coming toward us, and might merge with the Milky Way in the far future, the meaning of reaching Andromeda starts to bend in a different way again. Andromeda is not sitting there like a fixed target on a shooting range. It's moving, fast, and that motion completely changes what it even means to reach it. Right now, Andromeda is coming toward the Milky Way. Along our line of sight, it's moving inward at roughly 100 to 120 kilometers per second. That's on the order of 220,000 to 268,000 miles per hour. On top of that, it has some sideways motion across the sky. Put together, its three-dimensional velocity through space is big. That's why you sometimes hear the simple headline, "The Milky Way and Andromeda are on a collision course." For a long time, the story was, they will definitely crash into each other in about 4 billion years. Newer data from missions like Gaia and from Hubble-class observations complicate that. The sideways component of Andromeda's motion matters a lot. If there's enough sideways speed, the two galaxies might swing past each other rather than slam head-on. Current models suggest the chance of a direct, clean merger in the next 5 billion years is actually low, maybe under a few percent. Stretch the window out to 10 billion years, and the probability of a merger goes up to something like 50-50. So instead of a guaranteed crash, the future looks more like this. A strong interaction is basically certain on multi-billion-year timescales, but whether it's a direct, quick merger or a longer, more complicated dance is still an open question. Even if they do merge, your mental image of that collision is probably wrong. Galaxies are mostly empty space. Stars are tiny compared to the gaps between them. When the Milky Way and Andromeda pass through each other, almost no stars are going to physically hit other stars. What really happens is that the combined gravity fields get messy. Orbits of stars get stretched, tilted and mixed. Gas clouds slam into other gas clouds, compress and trigger new bursts of star formation. The central black holes of both galaxies can eventually spiral in and merge into a single, more massive black hole. From far away, it's a large-scale reshaping of two rotating disks into a more chaotic, merged structure. On the scale of individual solar systems, it's mostly a slow change in the background sky and the long-term shape of the orbit around the galactic centre, not a sudden wall of fire. So where do the Voyagers sit in this picture, on these billion-year timescales? Earlier we said Voyager 1 moves about 3.6 astronomical units per year, which is roughly 0.00006 of a light year per year. Over a million years, that's on the order of 60 light years. Over a billion years, about 60,000 light years. Over 4 to 10 billion years, you're talking roughly a few times that, tens to a few 100,000 light years in total drift relative to the Sun's original position. That sounds large, but remember the Milky Way's disk is about 150,000 light years across, and the distances involved in a galaxy merger spread over hundreds of thousands of light years or more. So in 4 to 10 billion years, the Voyagers have drifted some tens of thousands to maybe a few 100,000 light years relative to where the Sun started. Still well within the overall structure of the Milky Way's disk and halo. Still gravitationally bound. Still tiny compared to the size of the whole system. Andromeda, meanwhile, has been closing the gap at around 100 kilometers per second, reshaping the large-scale gravitational field. By the time the two galaxies are strongly interacting, the Voyagers are just small inert objects embedded in that overall flow carried along with the stars and gas. Now comes the subtle part. If the Milky Way and Andromeda do merge, does that count as the Voyagers reaching Andromeda? On a simple yes or no level, no. The probes don't steer into Andromeda's current disk. They don't hit its core. They don't lock onto a star system in that galaxy and arrive like targeted missions. Instead, what happens is that the distinction between Milky Way space and Andromeda space fades. Over billions of years, tidal forces and gravity mix the stars of both galaxies into a new larger system. Astronomers sometimes call the hypothetical remnant Milkdromeda, or similar nicknames. In that future, you don't really have two galaxies anymore. You have one big combined galaxy with a messy formation history. In that merged system, the Voyagers are just artifacts drifting in whatever orbit they've been shifted into by all the gravitational interactions. They don't migrate from one clearly defined galaxy into another. The galaxies themselves change shape and identity around them. From the point of view of an observer living far in the future, the Voyagers were launched from a small spiral component of an older, merged galaxy. Not from a cleanly separate Milky Way that still exists as an independent system, so as soon as you factor in Andromeda's motion and the possibility of a merger, the original question gets even weaker. There isn't a single stable target that sits at one position, waiting 50 billion years for a 1970s probe to arrive. There's a dynamic system where both galaxies are moving, interacting and maybe blending long before a Voyager-like spacecraft could cross more than a tiny fraction of the original distance between them. This sets up a key contrast. If you truly wanted to send something from here to Andromeda, in a way that makes physical and scientific sense, you wouldn't use a Voyager-class probe at all. and you definitely wouldn't rely on speeds of 17 kilometers per second. You would need a completely different propulsion regime, something that pushes you into a significant fraction of the speed of light, changes the whole time scale from tens of billions of years down to tens of millions. That's the bar you have to clear if you're serious about intergalactic travel, and it's the next thing we have to talk about. If you actually wanted to go to Andromeda on purpose with something designed for that job, the first thing you do is throw Voyager level speeds in the trash. 17 kilometers per second is nowhere near enough. You have to start talking about real fractions of light speed. Raise the bar to 10% of light speed. That's 0.1 c, which is about 30,000 kilometers every second, roughly 19,000 miles per second. That's around 1,760 times faster than Voyager 1's 17 kilometers per second. At that speed, every second you cross more than Earth's entire diameter. Now apply that to the Andromeda distance. Light takes about 2.5 million years to go from here to Andromeda. If you move at 1/10 of that speed, your ship needs roughly 10 times longer, so about 25 million years. 25 million years is still way beyond any realistic mission we can imagine, but notice how different that number is from the 50 billion years we got for Voyager. You've chopped the travel time down by a factor of around 2,000 just by going from Voyager speed to 0.1 c. That's the scale of change you need before Intergalactic even starts to leave the realm of pure fantasy and enter the outer edge of maybe one day with completely new technology. How do you even think about building something that fast? Concepts on the table today include beamed power light sails and advanced fusion drives. A light sail works like this. You attach a huge lightweight reflective sail to a probe and you blast it with an intense laser beam from a station back near home. The momentum from the light pushes the sail and accelerates the probe. Projects like Breakthrough Starshot talk about using this idea to push gram-scale probes to around 20% of light speed toward nearby stars. None of this is operational yet, but the physics is clear. If you can build the lasers and the sails, you can in principle get to significant fractions of c without carrying fuel on the ship. Fusion drives are the other big idea. Instead of burning chemical fuel, you fuse light nuclei like deuterium or helium-3, releasing far more energy per kilogram of fuel. Designs like Project Daedalus and later concepts suggest you might get ships up to 10% of light speed if you can solve the engineering. Again, none of this is something you can launch next year, but these ideas at least live in the same ballpark as maybe Interstellar, maybe one day Intergalactic, because they put 0.1 c or more on the table. Push even harder, toward 90% of light speed, 0.9 c, around 270,000 kilometers per second, and relativity starts to help you in a new way. At those speeds, time dilation kicks in. Clocks on board the ship tick slower compared to clocks back in the Milky Way. From the outside, you still need roughly 2.5 million years divided by 0.9, so a bit under 3 million years of cosmic time to cross the gap. But for someone on board, the journey would feel shorter because their proper time runs slower. It could, in principle, feel like a much smaller number of years to the crew, depending on the exact speed profile. That's the whole idea behind relativistic travel. You can't beat the speed of light, but you can play with how time passes for the travellers. Now slam that against Voyager. Voyager's 17 kilometers per second is about 0.00006 of light speed, or around 0.006% of c. To boost it up to 10% of c, you'd need to increase its speed by a factor of roughly 1,700. Kinetic energy scales with the square of the speed, so the energy needed goes up by about 3 million times. That's not a small upgrade. That's an energy demand so low that if you somehow tried to dump it into the Voyager bus, the spacecraft would just be destroyed. Its structure, electronics, thermal design, everything was built for a slow, gentle climb to 17 kilometers per second via launch and gravity assists, not for multi-million-fold energy boosts. And even if you had a super laser or a fusion engine, you wouldn't strap it to Voyager. The forces, heating and vibrations involved in ramping something up to 0.1 c or higher would rip a 1970s spacecraft apart. You design a completely new vehicle, probably small, probably very strong, with different materials, different layout, and entirely different systems for power, cooling and control. Voyager is an incredible mission, but it's built for the solar system tour and a slow cruise into interstellar space, not for riding a relativistic shockwave. This is the big reveal, hiding inside the simple question, when do Voyager 1 and 2 reach Andromeda? The honest answer is, they don't. Not in any way that matters. But the deeper lesson is this: the minute you seriously think about crossing between big galaxies, you are forced into relativistic propulsion. You either build something that goes a noticeable fraction of light speed, or the travel times land in the tens of billions of years range and become meaningless. So almost every serious concept for interstellar or intergalactic travel skips straight past Voyager-style speeds. Chemical rockets and gravity assists are fine for planets and maybe the very nearest stars over tens of thousands of years, but for galaxy-scale distances, they are non-starters. The question about the Voyagers exposes that directly. The gap between 17 kilometers per second and even 10% of light speed isn't a tweak. It's a totally different era of technology. Once you see that, the Voyagers slide into their real role. They're not prototypes for trips to other galaxies. They're more like markers. They tell you, this is what late 20th century humans could do. This is the speed range they owned. This is as far as they could push radioactive power and gravity assists. They're the baseline you measure future dreams against. Which brings you back to what they actually are. Not galaxy ships, but time capsules. They carry messages, those golden records moving slowly through the Milky Way's outskirts for millions, maybe billions of years. If they will never reach Andromeda as functioning probes, what are the odds that anyone, anywhere, ever finds those records at all? And if someone does, what will that really say about us? When you look at those golden records on the Voyagers, it's easy to slip into the idea that there are messages to the galaxy, maybe even to Andromeda. But if you actually run the numbers on what volume of space they sweep out, and what the odds are that anyone ever bumps into them by accident, the picture gets very sharp, very fast. Take that rough Voyager to Andromeda timescale we talked about, tens of billions of years at 17 kilometers per second if you pretend it could survive that long. Over 50 billion years of drifting at that speed. How much of the galaxy does a single probe actually sample? Not the whole Milky Way, not a big chunk of the local group, just a kind of thin streak. At 17 kilometers per second, you cover about 500 million kilometers every 10 hours, around 45 billion kilometers every day, and something like 15 or 16 trillion kilometers in 1,000 years. Turn that into light years and stretch it over tens of billions of years, and you end up with a path length of maybe a few tens of thousands of light years. That is enough to go from the inner parts of the Milky Way's disk out into the halo, maybe loop in partway around as the galaxy's gravity deflects the path, but it's still only a narrow track. The local group, the combined space of the Milky Way, Andromeda, Triangulum, and their halos, spans millions of light years across. The fraction of that volume a single Voyager sweeps out is effectively zero. Now think of probability of interception in a hard geometric way. Picture a civilization that only notices things that pass directly through their own star system, say within a few astronomical units of their star, roughly the size of our planetary zone. That volume is tiny, a small sphere a few billion kilometers across. Then compare that to the entire volume the Voyager travels through, over tens of thousands or millions of years, which is a long, thin tube in space, with a radius roughly equal to however close you'd need a pass to be to detect or capture it. The ratio between a single star system's cross-section and the total travel volume is insanely small. The chance that the Voyager just randomly passes close enough to one given star system at the right time for a local civilization to spot it without deliberately searching the larger volume is basically negligible. Multiply that by the number of stars it moves past, and the total chance of any random direct hit is still microscopic. It's like dropping a single grain of sand somewhere in all Earth's oceans and asking when a specific fish will accidentally swallow that exact grain. Now push that to Andromeda. Suppose there is intelligent life in Andromeda, with technology, telescopes, maybe even deep space probes of their own. What are the odds that one of the Voyagers, launched from the Milky Way, drifts unassisted all the way across and then passes directly through a random planetary system in that distant galaxy? Given the distances and volumes involved, that probability is effectively zero. Not just small, not just unlikely, but you would not expect it to happen even once in the whole history of the universe. It would need a ridiculous one-in-everything kind of coincidence. So if the Voyagers are not realistically going to dive straight into some alien solar system, is there any scenario where someone could still find them? Here's the twist that keeps the golden records from feeling completely pointless. A truly advanced civilization doesn't have to wait for things to hit their home system. They can go look. If some species, in the very far future, decides to survey their galaxy's halo and intergalactic surroundings in a systematic way, scanning for unusual small objects, they could in principle detect something like Voyager. What would it look like to them? Not a working probe. Long before they found it, the instruments would be dead, the RTGs cold, the transmitter silent, but the structure would still be weird. The metals are refined, the geometry is non-random, the isotopes in the RTG fuel are not in natural ratios. Even if the craft is partly eroded or broken, it would still stand out as a piece of processed matter, not a natural rock. With sensitive enough instruments, they could pick up the unnatural composition and shape, maybe by reflected light, maybe by close flybys with their own probes. In that kind of scenario, the golden record is not a message aimed at anyone specific or at any specific place like Andromeda. It's more like a tag. It says, something intelligent made this using nuclear power, metalwork and information storage at some point in the past. The record itself, with its engraved instructions and encoded audio and images, is a bonus, if they can figure out how to read it. But even if the disc is never played, the whole Voyager assembly already broadcasts its origin. This was not made by stars and gravity alone. So the real function of those records is not, we're sending a postcard to Andromeda. There are long-duration symbols. They say, for a short window of cosmic time, in a small spiral galaxy, on a small rocky planet, there was a technological species that could build machines, understand radio, and launch hardware into interstellar space. Those records are a physical statement that we existed and that we tried to leave a trace that outlives our own power sources, our civilizations, and probably our species. When you combine that with everything we've said so far, the picture sharpens. The Voyagers don't realistically reach Andromeda. They don't have the speed, the direction, the power, or the structural lifetime, but as they drift, they carve incredibly thin paths through the Milky Way's outer regions, carrying these dense, compact symbols of what we were at the end of the 20th century. That's their real job now, and that brings up one more tension you haven't fully felt yet. We've been talking about billions and tens of billions of years like they're just big numbers, but how do those spans compare to the entire lifetime of stars, or the future evolution of the universe itself? Once you put Voyager's hypothetical travel time next to those cosmic clocks, the mismatch between human time and cosmic time gets even more extreme. How do you even put Voyager's timeline on a clock your brain understands? Because once you try to line its trip to Andromeda up next to the actual age of the universe, the whole question starts to fall apart. Take the universe's history, about 13.8 billion years, and crush it down into a single calendar year, from January 1st to December 31st. On that scale, each month is a little more than a billion years, each day is tens of millions of years, each second is a few hundred years. In that compressed year, the Milky Way forms somewhere in late winter or spring. The Sun and Earth show up around early September. Complex life on land comes very late in the year. Dinosaurs die out on December the 26th. All of human recorded history, farming, cities, writing, science, everything, fits into the last couple of seconds before midnight on December 31st. Now drop the Voyagers into that. They launch in 1977. On this cosmic year, that's in the last tiny fraction of a second before the clock hits midnight and the year ends. Their entire operational life so far, a few decades, is less than a blink on this scale. By the time the calendar flips to the next cosmic year, the Voyagers have barely appeared and already gone quiet. That's how late and how short their story is compared to the universe around them. Next, compare their hypothetical Andromeda travel time to star lifetimes. A sun-like star lives for around 10 billion years from formation to red giant phase. Red dwarf stars, the small cool ones, can burn for trillions of years before they fade. Voyager's straight-line fantasy time to Andromeda is roughly 50 billion years. That's about 5 full sun lifetimes in a row. If the sun's life were a long, stable movie, Voyager's trip would run the whole film 5 times over. For the longest-lived red dwarfs, though, 50 billion years is just early days. They can keep shining quietly for 1,000 billion years or more. So from their point of view, Voyager's epic intergalactic trip is just one short part of their lifespan. And while that clock is ticking, everything else is changing. Over tens of billions of years, galaxies are not static backdrops. They slowly lose gas as it gets turned into stars. Star formation rates drop. Big stars burn out and explode or collapse into neutron stars and black holes. Orbits of stars get shifted by close encounters, by the pull of dark matter, by interactions with satellite galaxies. Clusters of stars can be stretched and mixed. If dark energy keeps dominating, the large-scale structure of the universe keeps expanding and spreading apart. A small aluminum and titanium spacecraft flying through all of this is not just fighting distance, it's trying to stay intact while the entire environment evolves around it on timescales that erase and rebuild galactic structure. Put that next to human time. When you say a long time, you usually mean centuries. 1,000 years feels huge. 10,000 years feels almost impossible to grasp. Voyager's Andromeda trip, even as a pure math number, is on the order of 50 billion years. Write that in centuries and you get about 500 million centuries. Every human event you've ever heard of, the building of the pyramids, the rise and fall of empires, the full stretch from stone tools to smartphones, fits into a tiny sliver of one of those centuries. Lay human history along that 50 billion year line, and it's thinner than a scratch. So when you ask, when will Voyager reach Andromeda, you're technically asking a question that has a numerical answer. But that answer lives on a timescale so staggeringly larger than anything in human experience that it stops behaving like a real when. It's more like asking, if I keep tapping a fountain with my finger atom by atom, when will I move it across a continent? In principle, every tap shifts a few atoms. In practice, the timescale is so far beyond anything meaningful that the event never happens in any usable sense. That's the real shock you're feeling under all these numbers. The issue isn't just that the answer is a very long time, it's that the answer sits outside the range, where words like before and after and soon and later even matter to creatures that live less than 100 years. Voyager is a short-lived machine from a short-lived species, trying to do something that would require outlasting stars, galaxies, and maybe the current phase of the universe itself. Once you see that, the original question needs to be tightened even more. We keep talking as if reaching Andromeda is a clear event, like you're arriving in another city. But on these scales, even the idea of a galaxy having a clean edge or a clear inside and outside starts to break down. So before you can say yes or no, you have to ask a deeper question, one that sounds simple but isn't at all. What does reaching Andromeda even mean, when galaxies have huge fuzzy halos, overlapping gravity, and a future where they might merge into one system anyway? Here's a problem nobody tells you up front. Before you can answer, when does Voyager reach Andromeda, you actually have to decide what Andromeda even is in a precise way, and that turns out to be messier than it sounds. On most posters and phone wallpapers, Andromeda looks like a neat flat disk, bright in the middle, fading at the edges, like there's a clean circle you could draw around it and say, inside is Andromeda, outside is not. In reality, there is no sharp border. The bright stellar disk is maybe 150 to 250,000 light years across, so that's the part you see in images, but the galaxy's dark matter halo and extended gas reach much farther, maybe out toward 1,000,000 light years or more from the centre. So if a spacecraft passes, say, 500,000 light years from Andromeda's core, is that in Andromeda or still between galaxies? There's no cosmic fence at that distance. The density just slowly thins out. Now place the Milky Way in the same kind of picture. Our galaxy has its own disk, its own halo of dark matter and old stars, and its own extended gas. The Milky Way and Andromeda, plus smaller galaxies like Triangulum, all sit inside the same larger structure, the local group. They orbit a shared centre of mass, and their dark matter halos overlap and interact. That means our galaxy is already feeling Andromeda's gravity and vice versa. In a strict sense, you're already living in a region where Andromeda's mass matters to the motions of things, even though the galaxies are still 2.5 million light years apart. So if you try to define reaching Andromeda as entering the zone where Andromeda's gravity starts to be important, you've already lost, because that's true right now. If instead you say, okay, fine, it means entering the region where Andromeda's pull dominates over the Milky Ways, you're now talking about an invisible boundary somewhere in the space between the two centres, roughly where their gravitational pulls balance. That balance point also isn't static, it moves as the galaxies orbit, as they exchange momentum with satellites, and as dark matter flows and evolves. It also depends on exactly what you count as mass, which is still being measured and refined. In the far future, if the Milky Way and Andromeda interact strongly and eventually merge, that whole idea breaks down even more. There isn't a clear Milky Way region and Andromeda region anymore. There is one large remnant galaxy with a central bulge, an envelope of stars, and a big shared dark matter halo. The part that used to be Milky Way and the part that used to be Andromeda are mixed. You can trace their origins in simulations and star motions, but you don't get a crisp geometric line in space you can point to and say, this side is Andromeda, that side is not. So where is Voyager in that kind of future? It doesn't fly like a plane to a city and park downtown. It stays on whatever orbit it's been given by all the gravitational nudges it's experienced. Today, that's a path out of the solar system into the Milky Way's outer regions. Over millions and billions of years, that path can be slowly bent by passing stars, by tidal forces from the changing galaxy, by the overall potential of the merged system if a merger happens. The probe will be bound to the big remnant galaxy either way, likely in some extended halo orbit, far from any bright central region, looping around slowly in a gravitational field that itself is evolving. There's no single arrival moment in that story. There's no day when a clock ticks and someone can say, the probe just crossed the official Andromeda border. Instead, there's a long, continuous drift in a region where labels like Milky Way and Andromeda stop being clean categories and turn into historical tags. From the point of view of a far future observer, the Voyagers are simply old artifacts orbiting in the outskirts of a big galaxy that formed from multiple earlier galaxies. Asking whether they are in Andromeda is like asking whether a specific water molecule in a mixed ocean came from one river or another. You can trace it in principle, but it doesn't line up with a yes or no boundary. And this is where the original question really starts to fall apart. We've already seen that the time needed for a Voyager to cross the original Milky Way Andromeda gap at its current speed is tens of billions of years, way beyond its power, its structural lifetime, and our own existence. Now add this, by the time such a span of time has passed, the shape of the local group, the identities of the galaxies, and the gravitational map itself will have changed so much that reaching Andromeda isn't even a sharply defined event. The separation we're talking about now is a snapshot thing frozen in our era. The universe does not keep that snapshot fixed while our little probe crawls toward it. So in the deep future, when someone asks, has Voyager reached Andromeda? You don't really have a clean yes or no because the galaxies we're talking about now have blurred into each other. Their halos overlap, their stars are mixed, and the probe is just another tiny piece of matter inside a much larger combined system. The question dissolves as the structures evolve, which leaves one last piece to put in place, the final direct answer people keep wanting anyway. We've gone through distance, speed, power, direction, environment, cosmic time, and even the fuzzy edges of what Andromeda means. If you pull all of that together and still force the question, so when do Voyager 1 and Voyager 2 reach Andromeda, what is the straight honest answer you give? So after all of this, if someone corners you and asks, okay, but seriously, when do Voyager 1 and 2 reach Andromeda, what do you actually say? If you force the clean, made-up, perfect straight line answer, it goes like this. You pretend you can rotate Voyager 1 in space so it points exactly at the centre of Andromeda without changing its speed. You ignore the fact that you'd need huge amounts of fuel and hardware it doesn't have. You lock in its speed at about 17 kilometers per second, around 38,000 miles per hour, and you let it fly. At that speed, to cover the roughly 2.5 million light-years to Andromeda, you're looking at on the order of 40 to 60 billion years of travel time. That's about 3 to 4 times the current age of the universe, which is around 13.8 billion years. Voyager 2 does even worse. It moves at about 15.4 kilometers per second, roughly 35,000 miles per hour, a bit slower than Voyager 1, so all the same math runs again, but the numbers come out a little larger. Where Voyager 1 might land in the 40 to 60 billion year band, Voyager 2's arrival time would be further out. Either way, you're nowhere near anything you can fit on a human timeline. You're just shifting around different versions of far beyond the age of almost everything. That's the clean numerical answer. But you can't stop there, because by now you know it's built on a pile of assumptions that are simply not true in the real universe. In reality, the Voyagers are not aimed at Andromeda. Voyager 1 is heading out toward Ophiuchus. Voyager 2 is going toward Telescopium. Andromeda is in a totally different direction in the sky. The probes have no large engines and almost no fuel. Their small hydrazine thrusters can adjust pointing, not re-aim the trajectory by tens of degrees. There is no realistic way to swing either craft onto a Milky Way to Andromeda intercept path. On top of that, their power systems are on a countdown. The RTGs are fading. Instruments are being shut down one by one. By somewhere in the 2030s, there likely won't be enough power to run even the radio transmitter. After that, from Earth's point of view, they stop existing as active missions. There's no way to track them in detail, no way to know exactly where they are moment by moment. They're just silent objects drifting in space, so the part of their lives that we can actually interact with, measure, and learn from ends within a few decades, not in billions of years. And then you have the big background problem. The universe is not a fixed stage. Over the tens of billions of years you'd need for a Voyager speed trip to Andromeda, the Milky Way and Andromeda are not sitting still. Andromeda is already moving toward us at about 100 to 120 kilometers per second along our line of sight, with some sideways component. The local group evolves. Galaxies tug on each other. Orbits change. Gas is used up. Stars are born and die. The clean 2.5 million light-year gap you're picturing now will not exist in the same form tens of billions of years from today. The map itself changes faster than Voyager can crawl across it. That's where the galaxy merger twist comes in. If current models are roughly right, then sometime in the next 5 to 10 billion years, the Milky Way and Andromeda will at least strongly interact, and quite possibly merge into a single larger galaxy. If that happens, the Voyagers won't arrive in Andromeda the way a plane arrives in a different city. They'll still be in orbits tied to the Milky Way's original mass, and Andromeda's stars, gas and dark matter will move into and through that same region. From the probe's point of view, space around them rearranges. Andromeda doesn't sit there waiting for them to show up. Instead, the structure we call Andromeda, today, comes to them as part of a new shared system. In that far future, asking, have they reached Andromeda? Doesn't really make sense anymore. The names change meaning. There's just one big remnant galaxy, with a complicated history, and the Voyagers are small relics in its outskirts. The neat Milky Way Andromeda separation you have now is a temporary feature of this era, not a permanent target line for a spacecraft. So what's left once you strip away the fantasy of a billion-year mission report from another galaxy? You're left with the contrast. You launched 2 spacecraft, each around 800 kilograms, full of 1970s electronics, tape recorders, and radio gear. You use chemical rockets and gravity assist to push them to about 17 kilometers per second, a speed that absolutely destroys anything you're used to on Earth. And then you discovered that, on the scale of even the nearest big galaxy, that speed is basically zero. The distance wins so completely that your machines might as well not be moving at all. That contrast is the real emotional core of the story you're telling. On one side, you have tiny human machines, built by a species that has only existed for a blink of cosmic time, running on decaying plutonium, sending data back across a one-day light lag, and dying within a few decades. On the other side, you have this universe where even the nearest spiral neighbour is so far away, and the timescales are so huge that 50 billion years of drift at Voyager speed barely counts. So when you get to the end of your video and you have to answer the title question out loud, you don't end with a big satisfying number. You don't say, they get there in 44 billion years, because that answer pretends that the direction, power, survival, and galaxy evolution problems don't exist. The honest ending is sharper, and it hits harder. You say, they never make it, not in any way that matters to us, or to them as functioning spacecraft. On every realistic clock, engineering, human, even stellar, they don't arrive. The Voyagers are not trips to Andromeda. They are signatures. They are small pieces of hardware thrown into interstellar space that say, to anything that ever finds them in any galaxy at any time, there was once a civilization here, on a small blue planet around an average star, that understood enough physics to do this and cared enough to tree. That's your final line. Not a countdown to a distant arrival, but a statement of what we've already done. We didn't send visitors to another galaxy. We carved our name into the dark as far as our technology could reach and let it go. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.